Thanks everybody for coming. Let's get started with this seminar. I'm very, very happy to have Pablo Moreno Muñoz. So I've collaborated with Pablo for many years now. He's a fantastic collaborator. At present, he's a research fellow in the Artificial Intelligence and Machine Learning group at the Universitat Pompeu Fabra, this Barcelona. He's one of the recipients of this very prestigious junior leader grant from the Fundación La Caixa. And he was telling me before, he was the only AI person that got this, or person working in AI subject that got in Spain and Portugal. Is it?
Yeah, it's like a foundation. It's like a private foundation that basically gives these starting grants. Usually is for life sciences projects and pure sciences.
Yeah.
And they are now focusing a bit more on these things that we do.
It's always very nice to see you, Pablo, and welcome.
Thank you. I'm really happy to be here today, the Center of AI. Thanks for the invitation to the organizers. And basically, the topic that I'm bringing today is led by curiosity. Oops, 1 second. Is this working? Yes. So Mauricio introduced me just to give you a bit more of context. I come from Madrid. I did my PhD, probabilistic machine learning topics. I was very interested back in the days on online learning. I was in Sheffield with Mauricio. Later, I spent some years in the north of Europe, in beautiful Copenhagen, working on certainty quantification, Bayesian neural networks, some approximations. And now in Barcelona, I'm trying to push, basically my own research agenda that is between a mix between this probabilistic modeling approach and self-supervised learning. That is something that interests me a lot, and is basically the topic that I'm bringing here today. So, yes, I think just before starting with self-supervised learning, I think more or less of us, we are aware why it's important, because it's basically the family of learning algorithms that push a lot the GPT large language models revolution. These tweets and kind of messages are a bit old. It comes from back in the days where we got this big shock with GPT-4, and it's like NLP researchers saying, oh my God, what I'm gonna do research now if this model is basically doing things fantastically. Both Philip Henning, Bernard Solkov, really pushing students to keep going. But some students are depressed how they can still get a PhD. Is it becoming pointless? Well, I think back in the days we were a bit on a crisis. I think my message is that we have yet many chances, and all of this is giving us opportunities to understand why things work so well and what we can learn from that. This is when things began to scale. Google, really a lot of parameters, when we began to see the difficulties that we have in the academic context to have these big models. This is like a few years ago, and also others, big PIs giving big messages. Okay, we should focus on this, on that, on some receipts to what we should pay attention to. So I am very happy about this message, or this tweet that Jan LeCun did back in the 2022 about, okay, one of the most important intellectual breakthroughs is self-supervised learning. I was in Europe a few years ago, and there was a beautiful workshop led by people from Berkeley, and particularly the computer vision guys. And somehow, some of them, they were claiming that they were one of the first ones to start with these sort of methods, this idea that you have an image and you have this surrogate auxiliary task where basically you take batches of images, you apply a transformation, and you are forcing your model to predict transform versions of your own data or features of your data. The reality is that self-supervised learning is a big family, very broad topic, more or less gets away from this unsupervised, semi-supervised, or supervised approaches with this idea that, okay, you have some data that is not labeled, you kind of construct your label to predict from pieces of your data, okay? Yeah, sorry about this, maybe it's a bit long, but we can take this definition of meta, AI lab. Basically, you obtain these supervisory signals, or what I said, more or less a self-made label, and basically we have this technique. You are forcing basically your model to predict on your own data by applying some transformation. And one of the simplest versions, at least for people who is interested in statistics, probabilistic modeling, or understanding things at the level that we usually do, we can we can start with mass pre-training. That is one of the simplest approaches. Basically, I think it came to the attention of the public because it was applied for BERT, this NLP model that Google pushed a few years ago. And we can assume that we have independent data. We assume independence across a lot of sentences, let's say. And we have sentences, and we assume that they are a 9-dimensional observations. Okay, I'm bringing here this 9-dimensional sentence where its dimension is a token. The Center for AI conducts fundamental machine learning research. So mass pre-training, for those who are not super familiar, basically you decide, you take a decision, and you set up a percentage of masking. Masking is just hiding some pixels, some dimensions of your data vector. In this case, we're assuming 33%. So we are masking 3 elements, and this goes in the iteration 1. And in the iteration 2, we randomly mask others, and so on. So the game that we have all the time per iteration is conditioned on the dimensions that are still visible to predict well basically the masking items. And then sorry about that, some equations moved. And basically, since we have the real value at the end to make a comparison, and then we have a loss. Okay, so we maximize all the time these log conditional probabilities based on these random items that we induce to ourselves in a way. And if we explore some of the early papers about what is this mass pre-training in a very simplistic way, we can basically write down the loss as this one. We are maximizing, optimizing the parameters of our model and maximizing this log probability with this M represents the mass, and this R is the rest of tokens. And very importantly, we are assuming here this M, for example, is the number. So in this case, will be 3. And very importantly, we are assuming conditional independence. This is important for the analysis. So we are not yet. I know that later there are other approaches more related to autoregressive models or more complicated that came later, more complex, that they assume conditioning between these guys. So you basically try to predict this one conditional. But in this case, I'm assuming here independence. That's where we have the sum. Okay, so it's basically a sum in this case of per iteration of 3 one-dimensional conditional probabilities. Okay, and yeah, basically you can think, okay, but this is NLP. How does this work? But we have a log probability on these weird symbols. Okay, usually in BERT and this model back in the days, they have these pre-trained encoders. So basically, they have something that has already learned some representation of your vocabulary, and it's basically, before doing this, is mapping every word, every token. I know that there is some cleaning operations, but it's basically mapping it to some real value data point or whatever representation you need. Okay. So basically, we can use a Gaussian, for example. Okay, something that is very important, and if you explore a bit on this, and it's not yet clear, is what is the correct number of mask tokens, or what is your masking ratio that you have to decide. I will add later, but I was very surprised when we presented this basically what came out of this work in Europe. I was very surprised that a lot of practitioners, engineers, yeah, I'm doing 15%, 20% is. They were fitting it heuristically. They have indeed detected that a range between 15% to 30% works well, forces the model to kind of learn some structure. But if you augment it too much, you are inducing too much missing data. So basically, you are not helping a lot, or you are making the task more difficult. And basically, the tools or the analysis that I'm going to present is going to help us to understand what is going on here as well. So, yes, for a naive statistician or someone that does have some experience with Bayesian inference statistics, if you get away a bit of all the LLM modeling and the engineering side, and you kind of extract the main concept, you can say, okay, we have here kind of a game that is prediction, conditional probabilities, generalization in the broad sense, in the sense that we are getting a good predictive performance in general that generalizes well to other types of languages, and random choices. So this is critical tools that we know very well in probabilistic modeling, and also topics related to Bayesian inference. So my question, or kind of my curiosity, is like, if there is something here that maybe we can extract or we can get. So I work a lot on Bayesian modeling, and I will explain later how I came out to these sort of things. It was more of a lucky moment. But I'm gonna try to link this mass retraining thing that I described to marginal likelihood. This marginal likelihood is basically very similar to the one that is lower bounded in the very famous paper of the VAs, of the Bayesian autoencoders. Basically, is your marginal likelihood where your latent representation of your data point is marginalized out, such that you have some log probability that is the sum of these independent log marginal units on every data point. The important thing is we're assuming independence between data points, but we are not. So we are assuming correlations and condition between the the dimensions of my data point xi. Okay, that we will discuss later. What is the dimension? That will be something between 10 and 500, let's say. So as I said, what I'm going to try to demonstrate today, and also to kind of catch your curiosity on this very basic type of self-supervised learning, is that maximizing this guy is indeed equivalent to maximizing this guy. So the relationship is we can compute it, and we can understand very well what is affecting the maximization of the other guy when we take decisions over here. So to do this, we need some math. It's not very difficult, but it's just a bit that is needed to go in order. So the first of all is, okay, here I'm basically taking one single data point. I assume independence between data points. I'm taking one single. So here I have all my dimensions up to the dimension. One very nice properties of probability is that we can apply this sort of factorization, this type of chain rule of conditioning that, okay, if I take this first dimension, I condition all the rest, basically this and this is equivalent, is equal, where I have now this log probability on the rest of the data points. This is very cool, and we can apply it. We can apply it recursively. So here, so I basically isolated this guy, and I repeated my operation, and I still have a lower dimensional log probability on the rest of the concepts. Okay. if we extrapolate that and we keep doing, we have something like this that for us is a sort of tool or a property that is used a lot, and we have this kind of chain of these sum or log probabilities. Univariate, this is very, very important. Univariate, where basically the number of conditional dimensions is reducing. Okay? And here you can see what is the pattern, right? I said before that this mass pre-training loss was this sum of univariate conditionals, and you can see here that we already isolated this property, and we are going to try to do a pattern matching. Something really interesting is the order. So we can apply this property. So we have basically a graphical model for every data point of dimension D, and basically we can decide in which variable in our graphical model we isolate and compute the rest of conditional probabilities in a lot of ways. Basically, in a combinatorial way. It's like there are a lot of combinations. And the big question is if there is a unique order. The answer is no. We can do indeed a lot of orders. And finally, they are all equal, the same. So in the end, this sum of all, basically having this d-dimensional graphical model, we can extract all these conditional probabilities. There are a lot of them and apply them combinatorially, but their sum of the log probabilities is always the same. So we can average and we have that value. And this is exactly what I'm doing here, right? This is the factorial, so it's basically all the combinations that we can get. So we have the sum of the univariate ones, and basically this P is the permutation. So let's say is the permutation is basically the order, or in the way that I'm taking these conditions. And the good thing is that this guy here, you can see that it's just the expectation over my permutation. And this guy is just the sum of the individual conditions. Very simple. Okay. So one trick that we can do is to reapply this same idea once and over on the rest of elements that we have. So what I'm going to do here is I did this. Sorry. I did this just targeting the whole vector of this log probability. I'm going to do a trick that is, I'm going to take the first one, isolate that one, fix, and apply the same trick on the rest of items. This is exactly what I'm doing. I'm choosing, I'm fixing this dimension 1, and I'm going to apply the same, basically the same reasoning to the rest, to the lower dimensional log probability of the rest of dimensions. Here you can say that the effect that fixing, when I say fixing, the effect that taking this dimension is very similar to this decision when we do on choosing masking units. When we mask, this is very similar. This is where the reason why I am doing this. And basically, what we can see is that this gives you a combinatorial problem that is very large indeed, but also gives you a sum. So here, basically having d dimensions, what is the t-1 decisions that I can take? But in the end, we can sum over all the averages, basically averaging over all these sums that we are doing over and over. I know that is a bit tricky, but and the result is clear. So what we can see here, what we have isolated is kind of the same. So this guy is the one that I presented to you. Is like I'm permuting all the dimensions that I have. I'm doing this average, and for them, I'm computing one-dimensional conditional probabilities given the mass the mask is the one that is basically selecting my dimension to compute the probability, and this one is the one that does the permutation. And here I'm also fixing and reapplying and summing all over the average. And you can see that we have indeed two expectations. We have here, this is the important result. So we have swapped the order of the sums. We have now that my log probability, my log marginal likelihood on my data point is just a sum for all the dimensions from 1 to d of one average and another average of one-dimensional probabilities, where this is just the ones that are in mass, and this is the rest data points. And this is basically the one that is operating over all the permutations. This number is super large, okay? Infinitely large, or almost very, very large. Depends on, I don't know, I think I did the calculus, so for 500 data points, if we are choosing 50 mass tokens, it gives you a number 10 up to the 92 or something like that. It's like a huge, huge, huge expectation, whereas this one is an expectation just over the mass tokens, okay, given the permutation. Okay. Having this result, as I said, we spot the pattern, and we can really draw this proposition that basically the cumulative expected loss of this mass pre-training loss, which is basically this guy here. Basically, what I'm saying is that this S is the one that is very similar to the mass pre-training loss, with the difference that we are summing along the dimensions. Okay, is basically equal to this expectation of this MD. And if you can stop if this is somehow confusing, I'm happy to rewind a bit or discuss. But basically, it's well, the big solution of this is that this is my empty, then my mass pre-training loss, because this mass is the one that I'm choosing. So here we are fixing and we let's focus on it here. We are applying mass pre-training with my BERT model or whatever. I'm choosing the 15%. This means that this M is a number lower than the dimensions. Let's say we have 9 tokens. I'm choosing 3. So basically, my loss, I'm trying to maximize this all the time. This index basically is the one over those 3 numbers, like the 1, 2, or 3, and this is the rest that is so easy. And as I said, the result is saying like, okay, basically the marginal likelihood of your data point is for all the values of the masking predictor. This is the very important result. So because yeah, this is the end that guides this loss. So basically, if we would like to do or to compute the marginal likelihood, the NPT loss, we need 1 to do this expectation, and 2nd to cumulatively sum all masking ratios from 1% to 100%. Make sense? This thing that I said. So it will be like this way of integrating all. Is how we will get this equivalence. And basically, this result, what this indicates, yes.
So you have focused on the form of this condition. Anything that you can say about theta? I haven't said much about.
No, yes, no, I haven't said. So theta is basically the parameter that we are optimizing in order to maximize this value. No decision taken on theta. Theta can be is basically the model that is learning the conditioning of between the dimensions of your data points. Basically, it can be any model. Yeah. Okay. So basically, the proof of concept to having this result, what we are going to do is test it from two sides. From the most simple probabilistic representation learning model that we can apply, where we can exactly compute the log marginal likelihood of these data points to see if really the result is correct. And from the other side, we are going to try to do on a small LLM to see if we spot the pattern similarly. So I start with this probabilistic PCA that, well, it's the usual case where we have some latent variable of some dimensionality k. We have a linear mapping between this latent variable that basically is the one that is generating on a higher dimensional space my data points, and we have some Gaussian noise. This is the model. And very importantly, we have our parameters, in this case, the ones Mauricio asked, the ones that we are learning is basically W, mu, and theta. In this case that we are optimizing, those are our thetas. Okay, we basically draw. This is very, I think we all know this. We have our data likelihood, so we can express the marginal likelihood of one data set of n data points as basically this product. They factorize, and yeah, we can also compute these predictive posterior probabilities in a closed form way. And this is very important because why I'm computing these guys? Because this is closed form conditional predictive conditions. Basically, this is if I have these log probabilities, so I have basically these probabilities of my mass, tokens, dimensions, condition to the rest. Basically, given this model, this is a closed form normal with some mean and covariance, and we know how to compute this perfectly in closed form. This areas. What I'm going to do with this, having all closed form, I can compute the log marginal likelihood. I can compute my log predictives. So using mass retraining and these conditionals, I'm going to see what is the effect, modifying things, particularly on the masking ratio, also on the number of permutations that I'm assuming, to see if this actually matches the log marginal likelihood described by the closed form log marginal likelihood described by the PPCA model, the well-known one. And now is where things began to be kind of fun. It's like an interesting analysis to me. So here, here I'm using, I want to see in the expectation, in the number of permutations, I want to see what is the effect on that expectation. Remember that the log marginal likelihood is the cumulative sum summing all across the different masking ratios of the expectation on the number of permutations, number of random mass of this log conditional probability. Here, I basically choose a small dimensional problem, 5 tokens, so a 5-dimensional vector. And this difference is the difference with respect to the log marginal likelihood. Here, I'm basically summing all across the masking ratios from 0% to 100%. And okay, you can see that is basically centered. There's no bias. So you are approximating better and better, converting as long as you are taking more and more random mass. Remember that this is the number that is combinatorial, that goes up to very large numbers. So this will convert and convert and convert up to the exact number of marginal likelihood for this case. Okay, you can believe me somehow in this case. This is exactly what I said. I'm basically playing with this number. Seems okay, seems center. And we are going to see what is the effect of increasing the number of tokens. Still that it still works, still centered. We have a bias estimator of my marginal likelihood by doing this cumulative mass pre-training. And this is when the fun thing starts, and where the part that took me more time in the past, really, I will explain why, but I really spent a lot of time to try to understand this. So before I the math very well. So if we now fix the 15% of my masking ratio, so I'm not summing anymore, I'm not doing a cumulative sum. So basically, I try to estimate my marginal likelihood by fixing the number of masking points. What we see is that, yes, for a very big number of tokens, it is obviously this sorry. Yes. Asymptotic result that is basically getting to this quantity, but is no longer centered on the log marginal likelihood value. Why? Because what we are getting is a bias estimate. We have a bias with respect to log marginal likelihood. In many cases, having a bias is a big problem because you are not targeting the amount that you want. So basically, I got really obsessed to try to control this bias and try to force a lower bound or an upper bound. This is what I wanted to understand. I wanted to understand, back in the days, if by controlling this bias with the masking ratio, I could induce a lower bound somehow, such that I could push. Yes.
Can I ask you something? Probably it's a stupid question.
Mm-hmm.
How does the bias pop up from going from 50 tokens to 512? Is it because we fixed the mask? Why is it? So at 50 tokens.
So here,
yeah.
How is going from this value to the other?
Yeah, what I'm saying with 5 and 50 tokens, it seems to me that it's unbiased, right? Because it's
yes, it's because, so basically the effect is because we are fixing.
Okay.
If we are summing here, each one of these values is computing the loss for 0% masking, 1% masking, etc., etc. We fix. In the moment that you fix, boom, you are out of an unbiased estimate. And okay, and I and also with the collaborators, we spent quite a time to try to force a bound because we wanted the bound for the things that we were doing. Not easy. We couldn't do, and before we understood why things going in this way. It is not actually a bound. It's not so easy, at least, to get one. I not got the result yet. This is exactly what was the response. So here in the previous case, I was summing. Basically, this sum is your master rating by fixing this. Okay, this seems interesting. What we can understand for this, remember that a lot of practitioners choose this masking ratio by hand because they observe better or worse performance. So what is going on? Okay, I'm gonna, now this very interesting curve is like, what is this area? What are we doing? I mean, it's fun. Basically, what we are doing is integrating the area under this, over this curve in this case. And basically, that blue area is the log marginal likelihood of your data point. And the sum of all of them of your data set. And basically, in this axis, you can see what is the NPT loss for each one of the mass totals. Basically, what you are seeing is this value S of theta for each one, for each value N, for each masking rate, etc., etc. In this case, for 200 tokens and for just one permutation. One permutation, I'm taking just one value in this expectation, just for one sample. Cool. So what happens if we take more permutations? You can see that the estimation of your area is smoother, okay? And you can integrate better. And And this is basically the things that we said. Okay, wow. So what I suspect is, what are you doing? If I take my decision to just select 30% and do it, is boom. And basically approximating this blue area with a flat rectangle is what we are doing. And that's the reason, because if you choose your mass ratio here, you have this rectangle, so the area is larger. If you are here, your area is smaller. It's not easy to be upper or lower, so maximizing, you are not having a bound to maximize. You can say to me, okay, Pablo, but it seems very trivial to see that up to here you have a bound, right? So up to here, I can say that you're going to be under, and in the other case, up. The problem, and this is very interesting, is what is the effect of my representation? Look how this changed when we augment a lot the dimensionality of my latent space of my representation. Things get a bit more tricky. And this is something that I'm very interested on. Indeed, in the NLP community, you are part of that. There were some papers interested in mutual information. They had estimators of mutual information, what is the maximizing the mutual information between my tokens, and concepts like this. Right now, there's also people that is exploring this connection between some information principles. Sven and I, my advisor, we spotted some relationships that are very interesting between the way that you are compressing in your representation in the latent space in the way that happens. Yes. What is K? What is K in this case? Well, I don't remember. I think it's in the paper. Will be a small, for sure. Yes, probably 2, 3 or something like that. Yeah. And you have a 200 dimensionality data point. And this is the reason why you can see how dependent on the latent space is basically to get a lower bound, because in this case, it's no longer up to here. So where is your decision? Notice. Probably, I mean, I hope that there will be some analysis and we can understand this better. At the moment, I don't have an answer, but I just wanted to show this this to you. Okay, let's all of this. Yes.
If you have a larger dimensionality of related space, you would expect bias to be larger.
That's a very good question. I mean, the bias is exactly the bias. The bias is induced by. I mean, it's related for sure. You're absolutely right, because you are inducing the bias but not integrating, not spanning over all the masking ranges. So you take a decision. I can't give an answer because it depends on the latent representation of your model and your masking range. But as we can see, probably yes, right? Because in this case, the area is much easier to be approximating in this range. Over here, when you have a more complex problem or learning problem, basically, if you are missing all of this, your approximation might be much worse. Or at least is what I can say at this moment. Okay, so far our parameters were untouched here. I'm gonna explain this later, but in this case the parameters were very well fit. We were computing numbers when the model is fit. So parameters are not random. Basically, are doing things in the way that they do. But if we initialize how this masking ratio affects to the learning, to the fitting of my parameters. This is basically, there are 5 curves because it's 5 different initializations. And convergence The black line is I know what are the correct parameters. So basically, it's the marginal likelihood computed for the optimal model. And basically, this guy here is the marginal likelihood, the exact one that I'm computing for the parameters that I'm training. So what I want is correctly reaches and converges to the optimal parameter. And basically, this stated curve is the one that I'm optimizing. What you can see is that in this case, I'm summing all over my I'm summing over all my masking ratios, but I'm just taking one sample. So that's why you basically see a noisy curve, mask pre-training, that converges. But always the marginal likelihood reaches what we want. This makes sense. We are basically maximizing what we want and obtaining the optimum. But the interesting part comes here, how this bias affects us to the optimization. That's very important. Biases can be a big problem in many representation learning problems, and you know to understand how that bias is affecting your optimization. And this is what I'm bringing here. Basically, here is your bias. What you can see is that it's not a lower bound. Here you can see better. This is the loss that I'm using for training. It's over. So instead of pushing my marginal likelihood over, is trapping, is pulling my marginal likelihood. We have a bias. Marginal likelihood is indeed under. But what happens? Why the marginal likelihood has the same shape as the noisy statements? Because basically the bias is independent of your parameters, of the optimization of the parameter. In this case. And also the convergence is not exact, but is well much better. In this case, basically, I fixed the mass ratio. I didn't write it down, but basically I fixed the mass ratio probably to 50% or 30%. There is basically your bias. And this sort of training is what gives me the main output of the project. So I think this very simple mass pre-training or self-supervised algorithms are basically maximizing these log probabilities, this log marginal likelihood of your data points up to a bias, and that's what they and indeed they optimize very well. This is something that we can discuss later, but this is kind of the main output. Yes.
So the log marginal likelihood, the solid curve, that's not from the sum, that's calculated from the parameters.
Exactly. Exactly.
Right.
It's
cumulative, but
exactly. You're absolutely right. I know that the experiment is perhaps not the most simple one or intuitive. So I'm basically training with this guy at every iteration and having some parameters, and in a surrogate model, independent of this optimization, I have a function and I'm computing and tracking what is the value of the marginal likelihood, because I can compute it close for the parameters at each iteration of this guy. I'm basically optimizing with this guy and I'm just checking what is the marginal likelihood at the end of this. Exactly what you said, right? Yes.
So is this all true still on this initial assumption we made of conditional independent between the master and the mass?
That's a very good question. This is something that is pending. I don't know. I don't have an answer. I suspect you can, and some results are equivalent, but then the way that you link, so basically in this proposition where I did the combinatorials, if you don't assume the conditional independence, things get a bit more complicated to get the.
So, but like, talking about intuition, intuitively, I'm feeling like the more mutual information you have between your mass token, the worse your bias is going to be. Because if you sample one, you then should be sampling the other one's conditional, or you're not. Is that the correct intuition for this?
Can you repeat that? Because this is very interesting. Can you see?
Intuitive, I'm thinking, like, if you have low mutual information for your math thing, then it doesn't matter if, like, I pick my third dimension. It then doesn't matter whatever I sample that, I just the ones saying. If there's high mutual information, then the other ones really should be conditionally on that form.
You're absolutely right. And this is something that we discussed back in the days. I think there is people looking to this from a different angle. I think your intuition is correct, yes.
So then taking that to its limit, if the mutual information was 0, that means the bias would also be 0.
Sorry, say that again, please.
If the mutual information in the mass token was 0, the bias also be 0, because you just go back to your perfect, not the likelihood estimation problem.
If the mutual information is 0, basically your bias, yes.
Which I mean, like,
No, I will try. I think this is very interesting because I thought about this indeed. Mutual information is 0. So basically, when you are learning, you are not capturing in the end after optimization any mutual information. So basically, any token can say anything about the condition.
mutual massive, you still have mutual information between the mass and the mass that you're still learning.
I think that's I'm we discussed. So basically, the spirit of this, or the follow-up works, is to get a bit more on this way of doing autoregressive self-supervised learning, to considering how this really makes when you have a strong other types of laws that basically compute these sort of conditionals and do that. This is what I wanted. And also patches, I think, also an adaptation. What goes on if you are with images and you take a patch, and which function is this still value? Because here we are applying these log probabilities directly on the pure dimensions. But imagine that we are applying rotations to force the model to learn some properties and to identify the dimension, even if there is a confounding function. How this math really reacts to this. Thanks for the comment, because I was really into this. Okay, here basically I tried the same results a bit with images, not with the PCA anymore. In this case, I could not compute. I used the elbow. So basically, what you can see here is with. Sorry about this. Maybe this is better to see the paper. But my message is, if you take a neural network, if you have some binary images, you are applying this kind of naive way of modeling. You are computing your elbow. You can see that basically your mass pre-training loss is doing kind of a similar convergence up to the elbow in the similar way as I presented before for the PPCA. I'm not the main fan of these results. I think there is still a lot to do. Basically, I did this just to check that I was not overfitting my conclusions to the linear models. And I just want to show you something that kind of the last experiments that are interesting, at least to me, is this phenomenon. So this was the curve that I showed you before, this area under the mass pre-training up to the values. What I'm showing you here is how this area, and this is related to the question that you said, how this area is changing as long as we do optimization. Basically, random optimization. Random initialization. So we have a flat area. Random parameters. Basically, the model has no information, so you have like a flat value. I think that you're right. This is what you said, right? If you have no information, imagine that you have nothing to capture. Everything is flat, so you can approximate very well a flat area with any point. And you are right. What happens as long, sorry that here this curve is joining here 100%, it should have been flat. Shouldn't go on. Okay, so basically, as long as you began to optimize parameters, what is going on? Your area begins to get reduced, so basically it gets augmented, and basically you began to convert to the true log marginal value. And in the end, you have this, okay, you have up to 15%, a very well high marginal value. Up when you begin to mask a lot of tokens, you decrease. And this is basically kind of the last view of this optimization. And this sort of curve is basically the experiment that I did with BERT. So this is with these language models. I wanted to see what was the effect of masking tokens. So if you basically take different tasks, different datasets. So if you take BERT for the language model, this very small one, with this mass arbitrary loss, initialize, it's absolutely flat. The loss is equal to all masking ratios. If you basically train it, and you take it, I think the student who did these experiments, I think he took the pre-trained tokens, so the pre-trained parameters, so having page or some repository, and you check your masking pre-trained loss, you see basically this sort of effect. That's as long as you mask more and more, you have this decrease. And of course, here the state changes a bit because we have a different model and we have a different parameterization and also latent space. Yes. So this is basically the conclusions or the ideas, curiosities that I wanted to bring to the audience. The conclusions that we did for this paper is we can confirm that this very simple way of self-supervised learning mass pre-training maximizes according to a stochastic gradient of the log marginal likelihood of the model up to a bias. If we take a masking ratio, we have understood what is the effect. We can now take some well-informed decisions on depending on which model or algorithm, but at least we can understand what is the effect of this masking ratio. And what I like more, these empirical results indicates to us that we can link well-known principles in probabilistic machine learning to these new ways of performing inference. So this work, I will show you later. We published the news, but this was kind of my last years in Denmark before moving to Barcelona, where it was a bit of an accident. I think if you are not aware of this paper, it's just a gem. I really love it. It's this paper that Chris Holmes for Oxford and his student Edwin Fong did. That is the connection between cross-validation and marginal likelihood is really beautiful and elegant. That this leaf P out cross-validation with some probabilistic posterior predictive score in the limit is equal to the marginal likelihood. And you can say, okay, some people, or I don't remember where I heard this or something, I think these ideas were in the community for a long time. Some people with a lot of experience were suspecting about this equivalence, but as long as I know, there had not been formally written. This is what they did. Fantastic paper. And even I love also this in the section, in the fabulous fifth chapter of the Gaussian process book by Carl and Chris Williams. They have this model selection marginal likelihood EPs, and they discuss these two big approaches of cross-validation and marginal likelihood. What are their their assumptions, what are their equivalences, and they give you some reference to the classes, well, etc., etc. And I think there is a very interesting that this issue has not been studied much empirically. I love that. And why I basically point to this? Because this result is what we started to work on different projects for Gaussian processes, and is the one that led us to the conclusion to understanding this type of self-supervised learning very well. So basically, the technique that I use to do this pattern matching, this equivalence, is a transposed version of the same result that they have in this paper, which is fantastic. Also, very interesting papers from Zurich, also Solkov, these equivalences, probabilistic models, self-supervised learning. There is some people that is getting really interested on this. I think if you want to join to these sort of models and approaches, fantastic. And this is basically the earlier paper that I did with Sven and Stevie, where we basically use this result on a Gaussian process latent representation. This is why I was already in the track of representation learning. And yes, my collaborators, Paul, which is now a PhD student in the Barcelona Supercomputing Center. We have like a big computer, is the National Center for Computation that we have in Spain. It's also part of this AI network that I think you also have in Finland and other parts of Europe. And Soen, that is a professor at DTU in the department that you can see on sunny summer. And he's also the EURIP's general chair this year. So I also use this space to say that if you feel like visiting Copenhagen and coming to EURIP's, it's a good moment. Registration is open, and I think will be a fabulous meeting. Thanks. And last but not least, come to visit Barcelona. We have Pompeu Fabra. If you have not heard of that, is one of our most prestigious universities in Spain. Barcelona has we have good funding, fabulous weather, food as well. And what is more funny, right now the Department of Engineering is built. Barcelona, as well as Manchester, was the old industrial, one of the first industrial parts of Spain, and they were indeed British who built factories for textiles and clothing. And we had in this old area of Barcelona these old British factories, and this is now my university, my campus. Like in Manchester, is lovely. And yes, this is all the results and kind of the paper that I'm promoting here, or is this one that went in EURIP's 2 years ago. And if you want to do your own research or you're interested, all results are 100% reproducible. And yeah, thanks to everyone for your time.